So let's try to use a polynomial or construct a set of polynomial basis on our same example, right? So that, just to write it down again. And a quadratic functional is that guy, all right? So we want to U, it's approximately U of H, Cj, phi j, and we're going to use a polynomial, so we're just going to say C1 plus C2x plus C3x squared. Now we have to make this thing satisfy the boundary conditions, right? So U at 0, if I plug in 0 into this equation, that implies that C1 equals 0, right? So if U1 equals 0, if U at 0 equals 0, and I plug that into the approximation function, that implies C1 equals 0. Right? So 0 there, those terms go away, and I just have C1 equals 0. Okay? U at 1 equals 0 implies, so C1 is already equal to 0, so I'm going to just say that's 0. Then I'm plugging 1 right there. Right? So 1 and 1, so that's C2 plus C3 equals 0. Or C2 is equal to minus C3, right? So when I plug that back in, my U of H becomes minus C3x plus C3x squared, or if I factor it, then I have this guy. All right, so let's, using that approximation, let's look at this again, okay? So I'm just going to copy everything down here and put in, so C3 is x squared minus x. So then when I compute the integral, I just have the function of C3 now. Right? So now I just have one equation I need to solve. Compute the derivative with respect to C3, and then solve that guy for C3. And then plot the solution. So it's clearly different than that, right? I use a different approximation, so, okay. So which one do you think is right? Well, they're both approximations, right? Turns out this differential equation we can solve, right? So it's, let's see, if we go d-solve minus d u of x with respect to x squared minus u x plus x squared to 0, u 0 equal to 0, u 1 equal to 0, x u x. Oh, I better use some, not a u, because I defined u up above, so it's, I better use v. So that's the exact solution, and we can plot that. So that's the exact solution of that differential equation, and that's the plot of it, right? So in the first example, where I just sort of arbitrarily pulled those guys out of my hat, it turns out I had some knowledge of the exact solution, so they were pulled out of the hat in such a way that they'd give me a better approximation of the exact solution, right? But usually, we don't know the exact solution. That's why we're using the finite element method, right? We're trying to come up with an approximate solution, and so we need a more systematic way of going about it, and thereby we'd use polynomials. Now, we could do something to help our approximation with the polynomials. What would that be? Yeah, either one, yeah. So subdividing the domain would require introducing elements, which we haven't got to yet. So for let's say we don't have that choice in our arsenal because we don't know what elements are yet. Increase the order of the polynomial approximation. So if we increase the order of the approximation, then we'd have more coefficients. The system would get larger, and then we could become a better approximation. So I didn't really plan to do that, and I don't have it in my notes, but you want to try it? Let's see if we can do it. See what happens if we increase the approximation order. So so let's just go back to a generic form. Say C1 plus C2x plus C3 x squared plus C4 x cubed. Okay. Now we have to make it satisfy the boundary condition. So u at 0 must equal 0. And we'll solve this for C1. I know I'm just doing it all programmatically. I know that's pretty obvious, but the reason is I want to make a substitution here. Okay. So then if I say u at 1 must equal 0, and I want to substitute in the solution, the first solution, and solve for C2. Okay, so now I have that. Okay, so then I'm going to say well, I'll just say u. Well, what can I do? U x is equal to u at x slash dot sol 1 slash dot sol 2 All right, let's do v or w. Okay, so there, I'm just testing out my function. I solve for the coefficients that satisfy the boundary conditions, and then I just plug those back into the original u1. I don't even have to do that. That's making it too confusing, actually. Let me, I can just do it in the quadratic functional. Right, so I just assume the polynomial, solve for the coefficients that satisfy the boundary conditions, and now I'm just going to substitute those in to this guy, okay? All right. All right, so then I have that, which has two unknown coefficients now, C3 and C4. So I have two equations. So then I can solve those two equations. What's going on here?
Oh, C1 and C2 are in terms of C3 and C4.
There we go. So a little better, right? And of course, I can go on increasing it, the order of the interpolation, until eventually it'll match exactly. But it's pretty close even with just a third order polynomial. Okay.